Right, good morning and welcome to this solution and explanation from NCRT Exemplar. This is the topic of ray optics and question number 9.9 in NCRT Exemplar of class 12. Now this question, let's read the question. So they were given an optical density of turpentine is higher than that of water while its mass density is lower. The figure shows the layer of turpentine floating over water for which one of the four rays incident on turpentine, the path shown is correct. So you have air, you have turpentine in this particular layer, and then you have water, right? Now, if you see the question, they have given four choices and they have four rays, which are related to the choices. The question is how the bending of light will happen at the refracting surface, right? So if you see there are two surfaces. Surface number one, this is one surface where the refraction is happening, which is bending of light. So let me just write it. Refraction is happening here. And then of course the second surface is this. This is the second refracting surface. Second refracting surface. Okay. We have to find out which path taken by the rays is the correct path. Now, if you think about these questions, where you have the word like optical density is nothing but the refractive index. And how do we go about solving these problems, right? That's a fundamental question being asked. Now, if you think about it, what we have to do is this, okay? The basic rule that you need to apply is this. So if you have a refracting surface or a layer, which divides the two medium, this is your medium 1 of refractive index N1. This is your second medium of refractive index 2. If the ray of light is coming from, so assume N1 to be a rarer medium, okay? Rarer medium, and the second medium is your denser medium, okay? Denser medium, optically denser, okay? Not the mass density. Ignore the word mass density. Always assume optical density in the questions of ray optics. So the ray of light comes, it strikes, right? It is coming from rarer to denser medium. Draw a normal at the refracting surface. The light will bend towards the normal, okay? It could have gone straight, but it turns towards the normal. This is your normal, okay? So this is your refracted light. So the ray of light came like this. This is your situation. This is a rarer medium. Draw a normal here, and the ray of light will bend towards the normal, okay? This is the way you need to look at it. So this is the and then this is a rule number A that you need to follow for rarer to denser. So rarer to denser, the ray of light bends towards the normal. Now let's talk about the situation number 2 and the rule number 2. The rule number 2 is if you have a refracting surface, and this is your N2 and this is your N3, okay, and this is again a refracting surface dividing the two mediums having different optical densities. The ray of light enters, so this is now a denser medium. It is reverse of the situation number A, denser to rarer, okay, denser to rarer. Draw a line which is normal, which should be perpendicular to the refracting surface always. The ray of light will bend not towards the normal but away from the normal, right? So normally we would expect if there is no refraction happening, the ray will travel straight, but it does not travel straight. Instead, it moves away from the normal. So this is your normal, this is your normal, and the ray of light is moving away from the normal. So this is your refracted ray, okay? So denser to rarer. If you look into the problem, and I will draw the diagram now of this particular question, you have in all how many? So let's say this is your container. So the container has two liquids inside it. So you have a container like this. This is your container, okay? Then you have a turpentine layer, and then you have water, and air is here, right? So this particular layer, the topmost layer, is all air, right? This is your turpentine, and this is your water, and it is given to you that the optical density of turpentine is higher than that of water. So which means the refractive index of turpentine, I will call it mu turpentine, this is mu water, and this is mu air. Mu air generally is taken as 1, so you don't have to worry about the values. What is not visible is, and we know that the refractive index of water is greater than that of air. So the refractive index of turpentine is greater than refractive index of water is greater than mu air, right? So you have these three known to you now, right? Because this helps you find out which particular medium is rarer or denser. So this is probably this is the densest medium, the turpentine medium. The second densest is this, and the most rarer medium is this. Now we will use the rules we learned here. The rules we learned here, which are these rules. Rule number A: if you move from rarer to denser, this is a rule number 1. The refracted ray will bend towards the normal. What will bend? The refracted ray. And in the case of denser to rarer, the refracted ray will move towards the away from the normal, right? So this is the case of denser to rarer. This was a rule number 2 we have learned. Now just let me tell you, I'm going to tell you some additional points which are outside this solution. First, obviously, I'm trying to clarify your concepts so that you can understand and have the logic in your mind. The second point will be, is how do you solve this numerical mathematically? That's another additional point which will come after this. So wait for that additional point. No channel, no application, no portal takes the trouble of explaining you physics. Physics without explanation is useless. Just watching solutions will not add any value inside you. You will get addicted to watching solutions without learning anything. So it is better to watch channels where you really get good experienced the solutions which are based on deep explanation. So always spend your time on deep explanation. That is where the physics foundation will get stronger. Let's go back. Let me just redraw this question. And then what we will do, we will use the rays. Light is always represented using a straight line, right, which is a ray. That is why we study ray optics or geometrical optics, right? So this is your water layer and that's your turpentine layer. So supposingly a ray of light comes in. So this is mu water. And I told you, I will tell you something which is more than this solution. Wait for that. Mu so this is mu air, right? We are starting with air, then we have mu turpentine, and this is mu water. So a ray of light comes from air like this. What rule will you apply? You are at rarer medium, you are moving into a very dense medium, right? Turpentine has the highest refractive index of all three. Draw a normal here. If you move from rarer to denser, you will bend, you will not go straight, like this, you will bend towards the normal. Okay, so this is your refracted ray. This is a straight line. It's a refracted ray. Okay, so this is your incident ray. This is your first refracting surface. This is your refracted ray. You're moving towards the normal. Draw a normal here. And now you're moving from denser to rarer because water's optical density is less. If you move from denser to rarer, you have to move away from the normal. This is it. So you can see clearly that this is your medium, which is rarer, then it is denser, and this is rarer. So first the ray moved towards the normal. This was towards the normal, the situation number A, rule number A. Then it has moved away from normal, situation number B, right? Let's go to the choices we have and compare this. If you look into this particular one, the water, this has come, draw a normal here, a normal, and then you can see the ray has moved away from, this has moved away from normal, which is wrong. And then in this case, the ray has moved towards the normal, which is wrong, because it's a violation of the rules we have learned. This is moving towards the normal, this is moving away from the normal. But we have already seen it is reverse of what is happening. So 4 is wrong. In the case of 3, no bending is happening, which is wrong. If the mediums change, the bending has to take place. If you look into first one, the first one we are moving from, okay, so let's say first one there is some correct okay thing that the refracted ray has moved towards the normal, correct? We're moving, and then if you see if you draw normal here, the incident ray is this. The refracted ray should have moved away from the normal, but it is bending in a very strange manner. It is not bending like this away, but it is bending, twisting like this, which is very strange. The one is also wrong. So the only logical choice is, now if you compare this, there is small bending towards the normal in 2, and then if you see the second refracting surface and the normal, there is a small bending away from the normal, right? Air, turpentine, and water. I hope this is clear. So the choice number 2 is the correct choice. I have explained this in great detail for the students who don't understand how do you solve problems of multiple layers of liquids on top of each other. I will not stop here. So don't go away. Wait for the next part of the video. We've already solved the problem. We know the answer is 2. But sometimes the numericals are more than this. And therefore it is important that you understand this part of it. The second part of the video is going to be now the mathematical part. How do you apply Snell's law? How do you apply Snell's law at such a situation? Okay, so the Snell's law at such a situation is applied like this. Okay, so you have layer number 1, layer number 2, right? And so this is your medium 1, this is your medium 1, this is your medium 2, and this is a general way to apply this. This is medium 3. Now we know how the ray will move. The geometric part is known to us. Okay, so let's say the rays move like this. Okay, so this is your, for example, this is some medium. It could be dense as compared to 2. So if it is dense, the ray of light moves away from the normal. It strikes the surface. Now it is, supposing the medium 2 is rarer as compared to the medium number 3. So the ray of light bends towards the normal, and then it strikes here. And assume now the medium number 4. Okay, this is your medium number 4 where you're coming out. The medium number 4 is rarer as compared to medium number 3. So you are again moving away from the normal. Okay, so you have already learned how do you decide whether the ray will move towards the normal, how the ray will move away from the normal. What I'm going to teach you now is the Snell's law, a form of Snell's law that you can apply to the multiple layers. Assume this angle of incidence to be alpha. Let this angle be theta. Correspondingly, this angle will also be theta because these two lines are parallel. Correspondingly, let this angle be beta, the angle of refraction. So this angle will become beta, and this angle, let it be gamma. Now let's start applying the Snell's law to this condition, and you will find this very, very useful when you're solving the problem. So let's say this is the refractive index of respective medium N3 and N4. One of the forms of Snell's law that you need to learn is what I'm going to tell you now is this one. Okay, just have a view of the diagram very carefully. N1, the refractive index of first medium, into the incident angle sine alpha is equal to n2 into sine theta. This is equation number 1. So this side is the incident side. The angle is included here. The refractive index is included here. Now this is a refracted side. Now this angle, this is a first reflection. Then there is a second refraction. It is n2 into sine theta is equal to n3 into sine beta. This represents the second refraction here. Okay. So let me just so to say draw a line just to tell you what I'm referring to. So this is where the second refraction happens. This is a place, and the first refraction occurred here. Now let me do one thing. Let me just draw the, okay, so I have a third refraction happening here. First refraction, second refraction, third refraction. So at the third refraction, if you see, angle of incidence is beta and the medium is n3. So n3 into sine beta is equal to the next medium n4 and the angle of refraction into sine of gamma. So this is 3. You can see I have created 3 equations which are very useful equations. Each one of them is a form of a Snell's law. Snell's law has been applied at each of the surfaces. Surface number, the refracting surface 1, the refracting surface 2, refracting surface number 3. This is the way ray has traveled. This is the way the ray has traveled. Medium 1, medium 2, medium 3, and then medium 4. 4 mediums, 3 reflecting surfaces. Apply the Snell's law at each of the surface, here, here, and here. And you can see it's very simple. For example, let me look at this third reflection. The angle of incidence is, this side is angle of incidence. The incident ray is contained in this medium. So the medium containing the incident ray multiplied by sine of the incident angle. And then the ray is moving into the next medium. So the refractive index of the next medium multiplied by the sine of the refracted angle. It's all across. This is the sine of refracted. So the right hand side is the refracted side. Refracted side. And the left hand side is completely the incident side. You can see the n1 is on the incidence, so incidence is happening, and sine of alpha, right? Alpha is contained in the incident side. So if you know these 3 equations, and what is the basis? If you see these 2 angles, theta theta, beta beta by geometry are equal. So if you know this geometry of alternate angles, between the 2 parallel lines, so this is your normal, this is your normal. So you can see this angle and this angle are equal. Similarly, this angle and this angle are equal. Now when you know this becomes a great advantage to you in solving these problems. How does it become great advantage? Now let me show you. If you know that n1 sine alpha is equal to, I'm referring to equation number 1, 2, and 3. From equation number 1 and 2, I can write n1 sine alpha is equal to this, and this particular equation, this one, I'm referring to this, which is same as this one, right, is equal to this, which means these 2 are equal, is equal to n3 sine beta. But n3 sine beta is equal to n4 sine alpha. So n1 sine alpha, sorry, this is gamma, is equal to n4 sine gamma. So the right hand side, which is a refracted side, becomes incident in the next layer. And similarly, this is the refracted side. It becomes incident on the left hand side. So what is happening? You have linked the first layer and the most bottom layer finally. So this was a first layer, right, where the incidence is happening. And this is where the ray is emergent ray, right? It is coming out finally. So the first layer and the last layer ray, right? So first layer, obviously, it was incident ray. And here what you have is the last layer ray, or the emergent ray. So you can memorize this. If you have multiple layers available to you, you know what is the refractive index here, and the angle of incidence is, for example, 30 degrees. And the last layer, that the angle of refraction, for example, here is 45 degrees, and the refractive index is n2. You can straight away write n1 into sine of 30 is equal to n2 into sine of 45. You don't have to worry about this at all. You can directly link the first incident ray with the last emergent ray. That's the way you need to solve these questions. I hope this made sense to you. We studied multiple things in this video, right? From basics to ray tracing, understanding the concept of moving from denser to rarer, rarer to denser. And then we applied the same concept to Snell's law. The Snell's law is a mathematical expression to make you understand how much refraction the light undergoes. And in the case of multiple layer liquid of different optical density or refractive index, we could relate the first layer with the second layer. And similarly, you can link any layer with any layer using this concept. These concepts are very useful for entrance examination. The last one which you studied, something like this, will help you solve numericals very fast, because you understand the geometry inside is nothing but the alternate angles being equal. The refracted sides are becoming the incident sides on the equation side of the things in 1, 2, 3, and therefore the first equation left hand side gets linked to the final refraction that happens at n4 into sine gamma. So n1 sine alpha becomes equal to n4 sine gamma. You're able to relate this to this directly, eliminating all other required calculations. It's a very fast way to solve the problems. This is the only channel in the country which is helping you with these type of explanations and numericals. You can go and watch any application, any portal, any paid classroom teaching. You will not learn anything close to what is being taught here at the comfort of your home. Without going to a classroom, you can get all your doubts cleared. Put your questions in the comment section if you like this, right? Yes, we like it. And give me suggestions on what you would like to see. I hope you are liking these videos and enjoying this video. My aim is to impact 1 million students and give them bright future when it comes to their career. Good education means good career. Good career means good life. An educated life is much better when lived properly. So I hope this is useful to you. Thank you very much for your time. Wait for my next video. Thank you.